Atomic radius sounds like a simple idea, but atoms don't actually have a sharp outer edge. Electrons live in probability clouds, not solid shells, so an atomic radius is defined by how close atoms get to each other in bonds or in solids. Different definitions exist, like covalent or metallic radius, but they all show the same trends because they reflect how tightly the outer electrons are held. What really controls atomic size is a tug-of-war between two forces. First, the nucleus pulls electrons inward. The more protons there are, the stronger that pull. Second, electrons repel each other, and inner electrons partially block the nuclear pull felt by outer electrons. This blocking is called shielding. To combine these effects, chemists use effective nuclear charge, written as Z effective. It's the actual nuclear charge minus shielding from other electrons. Higher effective nuclear charge means the valence electrons are pulled closer, making the atom smaller. Now look across a period, from left to right. Each step adds one proton to the nucleus and one electron to the atom. Crucially, those electrons go into the same principal shell. Because electrons in the same shell shield very poorly, shielding barely changes while nuclear charge increases. Effective nuclear charge rises, the nucleus pulls harder on the valence electrons, and the atomic radius shrinks. That's why sodium is much larger than chlorine, even though chlorine has more electrons. Going down a group is different. Each step adds a whole new electron shell. The valence electrons are now farther from the nucleus, and there are many more inner electrons providing shielding. Even though nuclear charge increases, the increased distance and shielding dominate. The outer electrons feel a weaker pull and spread out more, so atomic radius increases down a group. The trend isn't perfectly smooth, and the reasons are subtle. Electrons in s orbitals penetrate closer to the nucleus than p, d, or f electrons, so they feel a stronger pull. In the transition metals, added electrons go into d orbitals, which shield poorly but don't change the outer shell much, so radii change only slightly across the d block. In the lanthanides, f electrons shield extremely poorly, causing the lanthanide contraction, where atoms shrink more than expected. So the core idea is simple. Atomic radii change because size depends on how many electron shells are occupied and how strongly the nucleus pulls on the valence electrons. Across a period, effective nuclear charge increases and atoms get smaller. Down a group, new shells and shielding dominate and atoms get larger.